So the next talk will be given by Dr. Maicon Faria. Maicon is a specialist on HPC for scientific research applications with experience in deploying HPC solutions, software development and optimization, and expertise in intensive computational applications, especially in the context of GPU processing and engineering and science. And today, Maicon will share his experience with benchmarking, profiling, and porting to AMD GPU architectures and presents a couple of use cases. Maicon, the stage is yours.
Well, thank you. Thank you very much for the invitation. I will share my screen. Just, I think it's this one. Okay. The objective of this presentation is to share what kind of information a common developer will find for porting AMD porting applications to AMD GPUs. This is based on what people have available in the GitLab for ROCm, and also from AMD documentation. So it's nice the previous presentation, because we also get no information that maybe in the near future will be available for this other kind of developer that is not related to exascale project effort to port applications. So for the point of view of the, let's say, the little guy, or even these kind of developers from scientific application, that kind of thing, it's important, but sometimes they don't have access to all information about all possibilities that they have, and they have to rely on this on the information that I try to summarize here in this presentation. So the idea here is to present a little bit about the AMD GPU GPU evolution, the architecture evolution, the point of view of to know the acronyms and to know identify what we are talking. Also talk a little bit about what is available right now in the ROCm software stack, especially related to tools to add the development. Also talk a little bit about the HIP API, which I think it's important for someone which knows CUDA, have some experience on CUDA development, but it's starting at this point in the with AMD options. Talk a little bit about benchmarks to understand what we can expect from AMD GPUs, and talk about a little bit what we have available for profiling, for tracing, also for AMD GPUs, and try to compare what kind of options that we have with the options that we have for Nvidia, for CUDA in general. So, and at the end, I will just give some hints that I think are important for someone who are starting to port his code for groups who have some application, some scientific application. About the evolution of the roadmap for AMD, well, this is just part of the history. They are working with GPGPU for some time ago. But in this picture, we have this GCN architecture, then we move for the CDNA and then the CDNA2. They are building on that. Now, it seems that they are getting in a sensible path to that, and they are rushing to achieve the the same level of trying to reach the same level that NVIDIA provides us. We have older generation of GPUs who also had some GPGPU capabilities, and at some time ago we have OpenACC working well with AMD GPUs. That was very nice, but that was dropped, so it was a problem for the community, and now they are trying to regain the confidence of the general developers community and the scientific community also. So they are bringing right now to the market the new CDNA2 architecture. They have 3 new models, I think, that will be launched soon, or they are already deploying in big clients. I don't have access to these ones, so the benchmark that I will provide for this kind of architecture will be the ones that AMD provides, not the ones that I run by myself. But I tend to believe in them. And so here's an example of in the left we have a beautiful picture of a GPU showing 2 dies, and we have one schematic for the die showing the computing units, the distribution of memory controls, and also the infinite fabric introduced by AMD to integrate this device. To integrate, for instance, I have two GPU dies here, and they are integrated by infinite fabric, and also you can use infinite fabric to make communication between host and device. So, well, they have levels, hierarchies of memory, L1, L2 cache, and all the things that we are compute units. So all things that we are used in the GPGPU environment. This is the schematic of a computation unit. It's also something that is not that different from the paradigm from NVIDIA. We have some changes in the names. The tensor cores are replaced here by matrix cores. They do exactly the same thing. They help. They accelerate the matrix multiplication. That is very useful for machine learning algorithms. And they have also shader cores that are equivalent to the CUDA cores. And this is at the end is based on seeing the instructions. You have to look in your code for opportunities for coalesced memory access, all the things that we are use on CUDA development. So they also introduce capabilities for float point definitions that are getting popular right now, like half precision, bring floating points. They are not implementing the TensorFlow from NVIDIA right now. I don't know if they will do that in the future. So with that kind of floating point support, you can reach some different areas, from HPC, who relies a lot on FP64 double precisions, and also going to machine learning that use a lot of half precision and brain flow precision. So this kind of effort is good to attend all the different communities that will take advantage of these GPUs. So here, well, just just to comment, the difference is about some applications need more precision, other and not that much exponent range. So you can move from one to the other depending of the kind of application that you are trying to, the kind of simulation that we are trying to do. So in terms of raw performance, this is the data that AMD presents. You can see that it's quite impressive, the raw data that they present. Of course, these are, there's two things here. We are not comparing, for instance, we cannot compare that directly with A100 because of questions of price, that I'm not able to put that in the, to make some ponderation in price, because we don't have all information how much it costs. There is some estimatives, but that it's not that official right now. And we are, in the case of the MI 250 and 250X, you are looking to 2 dies, and A100, you don't have that condition. So we have to take that in account, but still, I'm a physicist, so the first thing that I look is for the FP64, the last column here, and here we see in terms of raw number, we see 4 times compared to a V100, well, sorry, to a A100. So this is quite impressive, and also for single precision and for half precision. You also have the information about the matrix, which is equivalent to the use of tensor, the tensor capabilities of the CUDA GPU. So it's quite impressive, the evolution of the AMD hardware in terms of raw performance. So here's the direct comparison, and between a A100 and a MI 200. So, but there is this thing, you are comparing things that have different prices, who are launched in different years, and also who are sometimes not the same number of die, the number of transistors is different. So you have to keep that in mind. Also, the Instinct GPUs also have more consumption in terms of energy. It's like 14% more. This needs 40% more watts compared to the Nvidia A100. So this kind of thing you have to take in account also. But for the developer who has the GPU available, someone paid for that, and you have to use, and then you can at least see what kind of raw performance are available for you. So in terms of integration, this is, well, this is very important. The integration of this GPU with CPUs and the communication between all these GPUs in node and the distributed communication also. So this is one of the topologies suggested by AMD for this is some kind of node, and this is both good for HPC and machine learning. So we can see that it relies a lot on the Infinity Fabric. Also, the green, the red, the black, and the blue communications are using Infinity Fabric. And there is a lot of communication also using PCI generation 4 lanes. And this is NVIDIA has the NVLink, so they are also providing things in the same environment. I don't have the information right now what they are thinking about because NVIDIA has the relation with Mellanox, and there is a software stack very consolidate the market. So I don't know what they are planning for these new exascale machines in terms of InfiniBand communication between directly communication using InfiniBand, direct communication between GPUs from different nodes using InfiniBand. I don't have the information what they are thinking about that right now. That it's important for strong scaling applications to run in exascale machines. So it's something that they must be concerned about that at this moment. I don't have information. And also the benchmark here for a small number of that we present here are for a small number of nodes. So sometimes we are just working with something that's not that stressed in terms of strong scaling. So this is something that also we have to put in mind when I move for the next and present the data that AMD gives. So, well, the benchmark will be some slides after that. So about the ROCm software stack, we have here in the first line, we have tools that are mostly related to the users can rely on that. Actually, in ROCm SMI, for instance, which replaced NVIDIA SMI, which is a good tool to understand what's happening in your machine. And the sysadmin tools would be the validation switch, data center tool, things like that. In the other column, the one behind, we have something that is very important, who are the ROC primitives for several scientific areas. Maybe the most important is BLAS. You have also hot rand for random number generator, FFT, and solver for EDEs, sparse for ROC sparse for matrix sparse algebra. So if your software can rely on this kind of libraries, not ROC BLAS itself, for instance, but for BLAS, and you can replace that directly, you can take advantage of the GPU with a very low effort. That's very important if your scientific application uses this kind of build blocks for scientific software. You are in a very good place to start, and ROCm's evolution it's supporting that. This is a great path to follow, but of course not everyone has this kind of facility. It's not that easy most of the times. Just another comment here, we have also MyOpen, which is in AMD equivalent for CNN, DNN from NVIDIA. The tool that is used under it's used by TensorFlow, Pytorch, everyone for the data, for the machine learning kind of applications. The compiler and tools, this is when things get, there is some good things there. There is things that AMD must put more effort to to try to be competitive in the point of view of a developer that's choosing a new architecture to port his software. So NVIDIA offer a lot of things, very good softwares who have very important capabilities that are lacking on AMD. Still, HIP. I will talk a little bit about that. HIP. It's a good API, and we have HIPify, which was a very good, very handy tool that allows you to port to convert CUDA codes to HIP code. That's very important. The debugger, they have the ROCm Debugger. I will talk a little bit after that, but it's a GDB debugger, which is not bad. It's the thing that you must have. There is profiler, the one that's the current supported by ROCm is the ROCprof. That's not very creative name, and well, they are in this situation. There is the programming models are OpenMP, HIP, and OpenCL, and the drivers and the distribution that are supporting are Red Hat / Ubuntu. In terms of applications and frameworks, we can see here. Well, the tools are not. We are already talk about that. The framework they are supporting TensorFlow, Pytorch. They offer Apptainer, Singularity containers that have out-of-box TensorFlow and Pytorch installed. That is very useful for users that just want to use the GPU from AMD. But the problem is that at this point, they are not compatible with the newest GPUs, not only the GPUs from the data center environment, the CDNA2, but also the RDNA, who are the GPUs that you buy for your home, for a small computer that you have to start development. Because this is a strong case for NVIDIA, is that you can do development in your machine. Of course, you don't have all the capabilities of a server, Tesla, Volta, Ampere card, but you you are able to make most of the work in your local machine. This is very important for developers. Math libraries, I already comment on that. Communication libraries, they are using UCX and library fabrics. They have support to OpenMPI and Pitch programming models, the ones that I commented previously. They have a Python who has a lot of support for ROCm. Well, and that's the picture, the general picture presented by AMD. Here is the one that I comment to you guys, is the TensorFlow apps Docker and the Pytorch Docker, you can run that using Singularity. So this is quite good. I use that to make some tests with AMD cards. This is very useful for users in general. Here is one example. I was testing the TensorFlow using AMD. What was the MI50, which is a GNC generation, so it's not a brand new one. Here you can just pull a Docker image with Singularity and run that. You have that flag, which is very important. So you expose your container to the AMD hardware, the GPU AMD, using this flag. You can use Python and run that. I will present that. This is just showing how to use it. I will show one benchmark using that, using the GPU, the AMI50 that I commented previously. Well, the HIP API, it's quite good. That model to have this mimic all the CUDA libraries functions. It's very good. They have so it works very well. I made some tests using Hipify. In general, CUDA code, it works very well. The only thing that most of the time you have to be concerned are compiler directives that are using CUDA-like information. So, and most of the time, the developers implement some kind of names in the directives that you have to check and to see if they are okay. But about the, if you look to the function conversion, as they choose API that most of the time just replace the name CUDA by the name HIP, things get very easy and these scripts work very well, this Hipify script. Programmers familiar to GPGPU will find HIP used to learn and use. So not about just the to change code from CUDA to HIP, you also have the same scheme, the same way of porting a code. You have to look for hoof lines. You have to understand coalesced access. You have to understand the memory hierarchy. And if you know that, you are safe and you can start to take advantage of a GPU, AMD GPU, for instance. Here, it's one example. You guys can, at first moment, rely that this resemble CUDA. You have a kernel, and the kernel is quite similar. You have allocation instead of CUDA malloc, HIP malloc, HIP main copy. So, and then you can launch the kernel via function, or even you can use the triple brackets that are very famous from CUDA. This is quite good to use. Here there is a documentation for the HIP API and a list, a reference between the conversion between HIP and CUDA. This is an extensive list. I think most of the CUDA library is supported. So at this point, HIP it's a quite good tool, and I very much recommend people to use it and to be confident about the HIP API. Here are the benchmarks results that I was talking with you guys previously. You can see Labs, which is a very used software in the community, people that work with theoretical chemistry, physics, so on, and other software that you have LinkPack. You have this, which is a classical sample code from Nvidia, the Anybot simulations. So making these tests, each one was chosen for some reason from AMD, so it's good to keep that in mind. And we see an improvement between the implementation using the most powerful AMD card against the Nvidia one. The software used on that are they are using conversions and optimization that are not available upstream yet. So most of the times you have some Git branch who has the AMD changes. Most of the time it's conversion of code between CUDA and heap. And also there is also a lot of applications. I don't think it's the LAMPS case, because LAMPS, as far I know, relies on Cocos. But the other applications, some of them are changes from, for instance, anybody, it's a converted to heap. So it's a quite straightforward change. And here we see as 2.5 speed up comparing the two GPUs. So, and there is also the link back, which is, it's quite important. So this is important to keep in mind. So they are presenting a good case about performance for the general community. Here is the test, the only benchmark that I have that I made by myself. This is a comparison between two AMD's MI50. This is a one die GPU compared to 4 V100, also one die. Here we have 4 GPUs, here 2. And we made some small testing using TensorFlow and this TensorFlow benchmark, where they are known in the community to test this kind of thing. And we see that, well, we can see that here we have one case. Here, more is better. And 4 GPUs, you have this number, 24,000, and with 2 AMDs, you have 14,000. So AMD, it's reaching a good performance here. I would say that AMD wins that. I didn't have 4 to test it, but if you do some easy calculations here, we can see that AMD it's quite good in this TensorFlow application. Well, in terms of profiling, what we have, the previous presentation that was there's some comments about profiling. What we have right now, it's a tool. It not yet support all the GPUs, and this is something that you have to keep in mind. All the counters are that will most of the time are not supported. So this is something that it's ongoing work that's not yet totally available for. It's not guaranteed that this profiler will fulfill all the developer needs. Well, but I'm confident that AMD will expand that in the near future. So it provides some counters. It's also capable of running traces, because there is another tracing application, but it's very limited, and this is very complicated because it does not provide a pretty output that you can have some pretty graph to understand what is happening in your tracing in your runtime. So there is a profile API that you can use to make annotations for a code. That's very useful. You can, for instance, make the trace for some part of the code if you want to check. You have to use input file when you have to add, for instance, here there is a lot of conversion between the names that you have on on Nvidia environment and compared to the names that you have in the AMD. For instance, wavefronts are warps, and I have a list showing how to convert that, and in the next slide. So you have also counters, for example, hits, cache hits, and cache misses, which are important to identify how is your code in terms of coalesced access, for instance. You can do that with multiple GPUs. So this is the kind of input that you have to use. There is several examples in the GitLab from ROCm that you can use to start to profiling some code. Here it's how to run that for a matrix transpose operation. So you generate a CVS. Here is the list of counters that you have for this Vega. This is not this is the MI50 technology. I don't know what they have right now for instance, the MI250 GPU. So that's something that will be changing and will be increasing in the future. You had hit and misses. Normally, you are, in the point of view of developer, you are looking to that in terms of profiling. Here it's the metrics that are defined over the counters that you have. And so here is the explanation of what is each of one of these these metrics. And this is also in the documentation. This is a very extensive list, and it's very important that the developer study that before using a profiling, because he has to know what he's looking for, what he will looking for to optimize his application. Well, for tracing, this ROCprof has in his API one thing called ROCtx. People that are used to Nvidia knows that there are that NVTX for annotation, which is quite handy, and they are implemented something very similar here. This is quite good to understand, for instance, the time for running kernels. But there is some issues that are very important. First, you cannot profiling concurrent kernels. That is very bad because, for instance, you cannot be sure using this profiling if you are using streams, not streams CUDA, the equivalent of CUDA cores, but streams from NVIDIA also, which are ways of increase the occupation of GPU when you have, for instance, MPI applications. And when you are doing real job in porting software, this is a kind of thing. This is the kind of thing that you want to have. I think it's possible to do implementation by your own, to using MPI. Also, they not supporting multiprocessing. Okay, so if you want to do things, real things, you have to add some time counting routine to see if you're using streams correctly. If you have some heterogeneous computation using CPU, GPU, you have to by yourself check if you are using asynchronous, for instance, copies between device and host correctly, or if you are not, if you are running parallel kernels also using streams, for instance, you have to do that by yourself and to check it. This is something that it's very important to AMD tackle that in the near future. So this is a big compromise for AMD. Well, in terms of tracing visualization, this is something that I learned for this presentation. This is strange because they are using for the visualization. What the profiler does is create a JSON file that you can open and see the trace using Chrome tracing. This is not very standard thing, but at least you can do that to see. And I don't know if there is other visualizations, other tools that can be used to that. Previously, they have Code XL, but it seems it's not working for ROCm 4.5. So that's something also that this is not that important, but for the general user developer, that will be something nice to have in the future. I hope that in a new presentation that I may do that, may update that presentation. We'll have a nice tool to make the visualization of the profiling, the tracings, and so on. The debugger is just a GGB, which are ROCm layer for that. It's simple, but it's something that's reliable. It's a good way to do things. It's good enough for in general. But of course, if you have something more, if you have, you cannot compare all the tracing, the profiling, the debugger with an inside environment from NVIDIA. So, well, there is something, but it's not at the same level. You have, for instance, a good tool in AMD, which is uprof, who doesn't have support to GPUs. Here you can see a debugger who also have counters, and you can do time. You can do a count. Here is the count of functions calls, for instance, and power usage. This one in particular, they have support the power usage of the GPUs, but this is just a small part. You want to have something more. So I hope, and I don't know if AMD is planning that they could move that ROCprof to be a backend for uprof and make these two as a presentation for the general developer. That would be very nice. I don't know if they are planning that. Well, we are quite fast here. I have my last slide. Well, so applications like most of scientific applications, not most, but it's decreasing the number, but still there is a lot of applications that are running in Fortran. I had some experience. I work with one called Nemo that we are trying to port, particularly using GPU, NVIDIA GPUs, and so that's where came some of my experience on doing that. So there's some advices that I would like to give. It's well, first about the ROCm AMD environment and Fortran. It's only supported by OpenMP right now, and I don't know if the support is complete. So in the old days, the GPU hardware, the GPUs were supported by OpenSCC from PGI. That was a great time for AMD GPUs, but that was lost, I think, in 2060. That support was lost. So for now on, if you my recommendation for let's say for the small guy, for the developer. Heap seems to be the good way to start. It's there is a lot of information about GPGPU development using CUDA that you can take advantage for develop it for right heap kernels, and also if you have old Fortran code, use C interoperability, because there is no explicit CUDA approach for development using Fortran right now that are available and that have some critical mass of people working on it. So I would recommend to use C interoperability to that. Heapify, it's a good tool. And also here there is a example. If you want to, I think that a presentation will be kept by most of people that are interested, and to check someone make some implementation using heap, Fortran, and using C interoperability. So for now, that's the kind of hints I would like to give to users to show how the AMD GPU's environment is right now, for if you are starting to plan implement a new software or port a software that exists, and you have to move for your small cluster or exascale machine, for instance. Thank you very much.
Hi, Maicon. This is Pascal. So I know that you mentioned MicroProf. So I remember Alexis and I had discussions because we had heard that MicroProf was going to try to get GPU integration, but because it's quite a nice tool.
Yeah.
Right. But it doesn't support GPUs now, and it's kind of a separate, because it's sort of AMD focused, not the AMD GPU group that's kind of doing it. There's this sort of separation. But so in working with it and also checking it, you haven't heard anything about GPU integration in the? I thought this was, I remember asking, it was kind of in the roadmap, or at least suggested roadmap, that ROCprof essentially will be stuck into MicroProf, allowing for GPU profiling. But you haven't heard about this either. No, I remember it was a vague thing that was a statement, and I was like, I wanted to get more information.
Yeah, I don't know what that billion-dollar organization have in mind, but this, to me, it seems to be logical to use move ROCprof as a backend for UProf, using that code as a backend for get information. But also you have to expand the ROCprof for that.
Yeah. I mean, I think they're doing it, right? So normally some of the counters are going to happen for the new cards, I guess, and ROCm 5. So the building towards ROCm 5 and the associated entire ecosystem. But it still looks like they're keeping it separate, and that's your impression as well, right?
Yeah, I'm expecting great news in the release, in the ROCm 5 release. So let's see what happens. And I think that maybe the scenario will change, because they delivered so much in terms of hardware. And
okay, but yeah, thank you so much, Maicon, again, and especially for joining us on this early morning at your end. It was really nice to have you here today, and with this important topic of looking, at all the tools available for AMD-based GPU platforms.